a series circuit, oh, sorry, worksheet 2, series and parallel. I just shot part of this video and I did this, I had to redo it because I did this as a parallel circuit. Anyways, a series circuit is constructed using one 1.5 volt battery and 2 identical bulbs. Let the resistance of the connecting wires be negligible. All right, so 1.5 volt battery, series circuit, one bulb, and I'll draw the other bulb down here. There's numerous ways to draw all circuits, but there we go. So 1.5 volts is our VBAT, we'll call it. Cool. Should have drawn a little bit more to the side, but whatever. What must the voltage drop across each bulb be and why? Well, in a series circuit, the bulbs split up the supplied voltage. So VBAT, I'm answering the question why. We'll go V1, I1, R1, V2, I2, and R2. All right. Each one has to split up the voltage. So each one of them is going to have 0.75 volts. All right. They have to add up to 1.5, and they're the same. So there's not really much to show there, right? You know just from the rules of the game that we're playing here that they both have to add up to 1.5. They divide up the voltage, and we don't have to worry about the wires. It says they're negligible. That wasn't true in the lab, but it is here. If the circuit draws 0.025 amps, what must the resistance of bulb 1 be? Well, the resistance of bulb 1 is going to be V1 over I1. R equals V over I. Well, we know that in a series circuit, right, I supplied has to equal I1 plus, and let me write this here, I supplied, all right, has to be equal to I1 plus I2. Or sorry, they all have to be equal. There's no branch offs, so the current flowing through bulb 1 has to be the same as the current flowing through bulb 2, and then back into the battery. You've got a constant flow of electrons, of charge going around this circuit, and there's no branch off, so it has to be the same everywhere. So then we can just say, okay, they all have to equal 0.025 amps, and we'll take that, put that back in for I1. So it's simply going to be 0.75 volts divided by 0.025 amps. R1 is going to be, run the math, 0.75, 30 probably, huh? Oops. $30 ohms. Should be more confident in my mental math. All right, if I took one bulb out of the circuit and reconnected everything, what would happen to the voltage across the remaining bulb? Well, it'd have to go up, because if there's only one bulb, then that bulb gets to dissipate all the power or all the voltage. It has this, doesn't have to share voltage. How about that? That's probably the way I should say it. So it would get the full 1.5 volts. All right, resistance would still be 30 ohms. That wouldn't change by taking one out. So what would happen to the current? Well, we'll see there. But voltage will go up to the full 1.5 volts. No sharing. No sharing of the voltage. You gotta have a voltage drop. So you go up by 1.5 volts through the battery, and then as soon as we hit another resistive element, we gotta start dropping voltage. And I can see ahead in the trail that there's no other resistor, so I have to drop it all across this one bulb. So the voltage across this bulb has to be 1.5 volts. What would happen to the current? Well, let's just do the math. I would equal to V over R. So since In a series circuit, the current is the same everywhere. I supplied will just equal I1. So I1, we know, is going to be 1.5 volts divided by 30 ohms. Let's see what we get. 1.5 divided by 30, and we'll talk about it conceptually in a second here. The current goes up. All right, the current goes up. Current goes up. Now I proved it mathematically, but why is it? Because there's now a less total resistance. And I'll show you that calculation below. All right. I only have to push charge through one light bulb to get back to the beginning. What must have been the total resistance of the 2-bulb circuit? So going back to the 2-bulb circuit. All right. So we have this thing we like to draw. I'm going to draw the 2-bulb circuit as just a single resistor. I'm going to call it REQ, which I'll write down here, equivalent resistance is what we call it in physics. It really means the same as total resistance. All right, the voltage of the battery is 1.5 volts. The supplied current is 0.025 amps. So this is an equivalent representation of the original 2-bulb circuit, right? We could think of these as just who knows what. Sometimes I like to draw it like a black box, the resistance that's attached to the battery, but we'll just draw it as a resistor. You can always determine the equivalent resistance of a circuit by looking at just simply the battery and how much current it's putting out. It'll always be the voltage of the battery divided by the current supplied to the circuit. So 1.5 volts divided by 0.025 amps. 5 divided by 0.025 equals 60 ohms. So the equivalent resistance here is 60 ohms. That's pretty cool. It's simply just, this one was 30 ohms. This one is 30 ohms. 0.025 amps, 0.025 amps. Simply add the two together and that gives you the total resistance. So these two questions kind of go together. The current goes up because the equivalent resistance went down. By taking a bulb out, we made it easier to push electricity through this simple series circuit. All right? Electrons only go through one bulb. If you track just one electron moving through the circuit, one little bit of charge, let's say, all right, it's going to go fly through here. It's going to have to go through this bulb and this bulb. So that's twice as hard for that electron to make it around the circuit. It faces 60 ohms of resistance total. So you got to follow just one little bit of charge when you think about equivalent resistance. And I really should be thinking of conventional current, just one little bit of positive charge, but that's not what really happens, is it? All right, this next page is a little practice here. So resistors in series add together to form one large equivalent resistance. To figure out the equivalent resistance of a series circuit, we just add the resistors together. So 60, 40, 85. I've been meaning to cut this question out of here for a long time because it's already drawn here. I'm just going to add the numbers to it. 0.03 amps, that's our I supplied. V bat, all right, we don't know. We'll say R1 is 60 ohms. We'll say R2 is 40 ohms, and we'll say R3 is 85 ohms. All right. So what we're going to do is basically figure out everything about this circuit. And I just like writing right on the picture to keep things straight. So the rules tell us a lot of things, but let's just go through this one at a time here. Question. So diagrams of the circuit, see above. Again, I've been meaning to take that out of there. I just keep forgetting to do it. Determine the equivalent resistance of the circuit. So Req is going to be R1 plus R2 plus R3. So 60 plus 40 plus 85 gives us 185 ohms. Now I'm modeling bad problem solving. I really need to plug the units in there at least once. So the equivalent resistance of this circuit, simple series circuit, is simply 185 ohms. Voltage of the battery, well, again, remember what we said on the previous page, we can always couple together equivalent resistance and voltage of the battery. So I could represent this circuit as just simply a cell. You know what, I'm going to use the black box here. I'm going to call it Req, right? That box represents all of the resistors up here, right? And I supplied. So whatever the voltage drop is across the equivalent resistance, that's what the voltage of the battery is. So really what I'm doing is I'm finding the voltage drop across the equivalent resistance here. So rearrange this, you get V equals IR, and I'm not going to put all the labels on here. The voltage of the battery would have to be 0.03 amps times the equivalent resistance of 185 ohms. That would give us 0.03 times 185 equals 5.6 volts. 2 sig figs is what I'm going to do here. No more. All right. Now, determine the voltage drop across each resistor now. Okay. Sum the individual drops to disagree with part C. We already know that each of these voltages, they have to add up to equal our supply voltage of 5.6 volts. And we also know that the current through all of them has to be the same. So 0.03 amps, 0.03 amps, 0.03 amps. So let's go ahead and get all the voltages down here at the bottom. So V1 is I1 R1, so it's going to be 0.03 amps times 60 ohms. All right, that's going to give us 0.03 times 60 is 1.8 volts. V2 is going to be I2 R2, which is going to be 0.03 amps times 40 ohms. It's going to be 1.2 volts. And the last one there, V3, is I3 R3, 0.03 amps times 85 ohms. Now this one's a little bit weird. 0.03 times 85 gives us 2.55 or 2.6. And the law says, right, V bat better darn well equal V1 plus V2 plus V3. And again, I'm getting that from series circuit here, right? Currents are all the same. The voltages all have to add up to the voltage of the battery. And look, does it? 1.8 plus 1.2 is 3, plus 2.6 is 5. So 1.8 volts plus 1.2 volts plus 2.6 volts equals 5.6 volts. Hey, it checks out. All good. Why shouldn't I have put a check mark there? That's silly. I'll have to make it look a little bit different. Checks out. That's terrible. Anyway, conservation of energy, it reminds me of. Right? We already talked about that during the lab. All right, on to the parallel circuit here. All right, this one's a little different. So 1.5 volt battery, 2 identical bulbs, okay. So I'll try to draw this one a little better this time, center it a little bit better. My carpal tunnel is screaming right now, but what are you gonna do? 1.5 volts, that's our V bat. All right, so the laws of a parallel circuit. Why don't I write them over here? That would probably be smart. Equals V1 equals V2. And how is current gonna I1, I2, V1, V2, R1, R2. I supplied equals I1 plus I2. So that's how the rules are going to apply here. So in a parallel circuit, the current splits up, you know, it recombines down here. The current is the thing that gets divided, not voltage. They all have the same voltage because they're all connected directly to the battery, right? This whole thing, this whole side of the circuit is all positive. This whole side is negative. They're all attached directly to the 1.5 volt battery. What much the voltage drop across each resistor? Well, V1 equals V2 equals V bat. They all equal 1.5 volts. Why? Well, because that's the rule. They're all connected to the battery. If the current circuit draws 0.1 amp, what must the resistance of bulb 1 be? All right, so R1 equals V1 over I1. That's going to be, well, 1.5 volts divided by the current through bulb 1. Well, how do I know what the current through bulb 1 is? Well, let's take a look here. Well, I sup must equal I1 plus I2, so 0.1 amps has to equal these two. But since they're identical resistors, they have to be the same. I1 and I2 have to be the same current. Current takes the path of least resistance. So when the current gets here, when the charge gets to this junction, it's got to make a decision. Am I going to go this way or am I going to go this way? Well, if one goes this way, the next one goes this way. The next one goes this way, the next, and they, you know, the current gets split up evenly because the paths are the same resistance. So each one of these would have to be 0.05 amps, 0.05 amps. So we can do our full math here now. R1 is 1.5 volts divided by 0.05 amps. I think that's going to be about 30, is that right? 1.5, oops. 1.5 divided by 0.05 is about 30 ohms. Very good. If I took one bulb out of the circuit and reconnected everything, what would happen to the current supplied by the battery? All right, so if I took one bulb out, that would leave me with one bulb. All right, so just kind of think about this, draw it real quick. Still going to have 30 ohms, still going to be 1.5 volts. Let's just see what the heck the current would be. I would equal V over R, since it's just a simple circuit. It's just 1.5 volts divided by 30 ohms. That's going to be 0.05 amps. The current supplied by the battery went down. And it's the same as what the current through one of the bulbs would have been. So when we put bulbs in parallel, it doesn't impact the bulb before it, right? This one just starts draining the battery more and more and more and more. We did that question on the power worksheet where we had 30 light bulbs in the circuit, right? In parallel, each one just draws the same amount of current here because of the same, the same bulb. The battery has to keep up with that. So if you take one out, now the battery doesn't have to supply as much, so current goes down. Well, what happened to voltage across your remaining bulb? It'd stay the same. Still connected directly to battery. Put another one over there, no different. What must have been the total resistance of the two bulb circuit? So we're going to do our little black box drawing here again. REQ. All right, so now that black box is taking the place of the two bulbs. V bat. All right, and I supplied. All right, so I supplied comes in, goes through this resistance, comes back out. So that box is literally like putting a box around these two bulbs up here. And okay, what's the total resistance contained within that box? Well, REQ is V bat over I supplied. R equals V over I, so 1.5 volts divided by, now it's the 2-bulb circuit. We're going back up to here now. 0.10 amps, that's 15 ohms. So check this out. Two 30-ohm resistors in parallel, all right, turn into a total resistance of 15. So it's almost like, are you adding them together and dividing by 4, or are you just halving one of them? What's the math here? This is kind of funny. It's like you're halving it by adding another path, and that's what you're doing. See, total resistance goes down as you add more bulbs because you're giving more paths for the supplied current to split up through. All right, it can travel a lot faster. Like, and this is why wires get hot when you put too many things in the circuit, right? Like, the battery has to pump out more and more electricity, more and more current as you add more in parallel. This little teeny wire here, right, is now got to supply current for every single item that comes after it. We'll practice with that over here real quick. Resistors in parallel add together to form a smaller resistor. The equivalent resistance will always be less than the smallest resistor value. So, you know, if this is 60 ohms, which we're going to say it is 60 ohms, we're going to say this is 40 ohms. So we're taking those same resistors. We're going to say this one's 85 ohms. Great, my light shut off. All right, hold on a second. All right, so we're going to take those three resistors and put them in parallel. Well, if I just had a 60 ohm resistor, all the charge has to move through that 60 ohm resistor. I add a 40 ohm resistor, that's like opening up another lane of traffic. Now, it's not as smooth of a road as this first one, but it does allow some more traffic through. And I add another 85, well, another resistor, that opens up a third lane. You know, this is a nice smooth road. This one's actually even better, the 40 ohm resistor. The 85, this is a pothole covered lane or something, right? But, you know, I got 3 lanes of traffic now, so it's gonna be easier. So every time I add a resistor in parallel, the resistance goes down and down. So how do we deal with this mathematically? Well, this is the equation. So, draw a diagram of the circuit. We already have the diagram. I really need to get rid of that. 6.0 volt battery this time, VBAT. I supplied is here. All right, this will be I1, this will be I2, and this will be I3. There's an intermediate current here, right? Like this current here is going to be I2 and I3. The current through resistor 2 and resistor 3, this intermediate, and it's the same as the current here once they recombine. We don't label that. I'm not going to label that. Actually, what's kind of interesting here, this is kind of neat. You could draw this resistant, you could draw this circuit differently. I could have drawn it like this. Some kids like this kind of thing because this is a terrible resistor in the middle here. That's embarrassingly bad. I apologize. Oh my, it's only getting worse. All right. I supplied comes into here and it splits 3 ways, recombines down here. So I1, I2, and I3 are all, it's a little bit easier to see how they're connected, right? That's probably how you, more like how you would wire it up in reality, but moving this wire, flattening it out, and drawing it like this it's the same thing. These are equivalent drawings to one another. Very bad one there, but anyways. If you just look at the solutions, you're not going to be like, what the hell is that drawing for? Anyway, determine the equivalent resistance of a circuit. All right, 1 over REQ equals 1 over 60 ohms plus 1 over 40 ohms plus 1 over 85 ohms. Now, here's the deal with this. You got to add these fractions, all right? You got to add them. So 1 divided by 60 plus 1 divided by 40 plus 1 divided by 85 equals 0.053. I'm not going to put units on this. It'd be 1 over ohms, the units. So what I have right now is 1 over REQ equals 0.053. So now we got to solve for REQ. REQ equals 1 over 0.053. So 1 divided by 0.053 is 19. 19 ohms is your equivalent resistance. Always has to be less than your lowest value. The closer they are together, like if it was 60, 60, and 60, the equivalent resistance would be 1/3 of 60. It'd be 20. It'd be different. You know, so the numbers get skewed depending on what we got here. If it was 40, 40, and 40, it would be like, I don't know, 1/3 of 40. 12 or something. All right, 13, I guess. If I'm gonna plug this into my calculator, what I actually do is I just immediately do 1 divided by 1 over 40 plus 1 over 60 plus 1 over 85. I just do it all in one step. I literally just do it as, I take the inverse of the whole thing right off the bat. Alternate solution, we'll call this. I'll do REQ. Okay, 1 over REQ equals 1 over 60 plus 1 over 40 plus 1 over 85. If I take the inverse of both sides immediately, I get REQ equals 1 over 60 plus 1 over 40 plus 1 over 85. You don't invert them individually. You have to invert the whole sum. All right, you have to write it like that, and that's the way you have to put it in your calculator. So what I put in my calculator is 1 divided by 60 plus 1 divided by 40 plus 1 divided by 85. That's what I'm actually putting in my calculator. And the calculator spits out 19. All right. Determine the current across each resistor. Okay, now this is going to be a little work. All right, notice it didn't ask me about the voltage because I know they all have to have the same voltage. So I1 equals 6 volts divided by 60 ohms, which would be 0.1 amps. I2 is 6 volts divided by 40 ohms, which 6 divided by 40 is 0.15 amps. I3 is 6 volts divided by 85 ohms, which is 0.07. Now, I'm gonna have to keep this, I'm just gonna make it 0.07. I don't wanna add another decimal here, 7.1, but we'll get rid of it when we add anyways. It says, okay, determine the current supplied by the battery. So there should be, according to the rules, right, all three of these added together, 0.10 amps plus 0.15 amps plus 0.07 amps. So 0.1 plus 0.15 plus 0.07 gives me 0.32. Now, that's great. And I'll do an alternate solution, another alternate solution. All right, another alternate solution. I could have said, okay, done my black box thing here. This is 19 ohms. This is 6 volts. I supplied equals 6 volts divided by 19 ohms. So I did my equivalent circuit here. So 6 divided by 19 gives us 0.32. So whatever makes sense to you, is good with me. All right? All right.